is weakly acidic. Okay, so when phenol it reacts with sodium hydroxide, a base, it gives sodium phenoxide. That shows phenols are acidic in nature. Phenols are more acidic than alcohol. Okay, now this acidity is because of nature of this hydroxyl group. We have to compare. Alcohol also contains hydroxyl group, phenols also contains OH group. So this OH group now is attached to an aromatic ring, so its nature changes, and that's why due to resonance, the effect of resonance, this phenol is more acidic than alcohols. In alcohols, aliphatic alcohols I am talking about, in aliphatic alcohols we cannot see, or there cannot be such a type of resonance possible. That's why phenols, they are more acidic than alcohols. Okay, now there is a lone pair of electron present, two lone pairs of electrons present on this oxygen. So it shares one of the lone pair with a neighboring carbon, and this double bond, or the electrons which are utilized for formation of this double bond, they migrate to this carbon. So your first resonance structure will look like this, where oxygen is now double bonded with now only one lone pair is remaining with oxygen, due to which there is positive charge on oxygen, negative charge will be here. Okay, this is first resonance structure. Now this negative charge in the ring is further stabilized. How? This negative charge, or the electrons, extra electron present on this carbon, will be utilized to form a bond between these two carbons. The electron in this bond, they migrate to this carbon. So the third resonance structure will be like this. Similarly, this bond, or the electrons, they are used to form a bond between these two carbons, and electrons in this carbon or this bond, they are migrated to this carbon. So the next resonance structure will be like this. And the next one will be, this electron is used to form a bond between these two carbons, and electron present in this bond, they are migrated or given back to oxygen. So it forms again structure of phenol. This resonance stabilization is possible, and that's why when I say there is a positive charge on this oxygen, it can easily donate this proton, because the entire structure is, or the charge is, resonance stabilized. If we compare this resonance stabilized, if we compare this structure with alcohol, for example, I take methanol. Now in this case, this carbon in methanol is sp3 hybridized, and if we look at the resonance structures, this carbon is C double bond OH, and in this case it is sp2 hybridized. So sp2 hybridized carbon, why phenol is more acidic than alcohol. Now when the proton is released from this phenol, the phenoxide ion, whether it is stable or not, that also will decide the acidity. So the phenoxide, which is formed after loss of proton, okay, it is also resonance stabilized. How? Let's see. Now remember, when you draw phenoxide, now it will have 3 lone pairs of electrons. Okay, now just because it has lost one proton and electron from that hydrogen is now with oxygen, so it will have 3 pairs of electrons. Okay, now one of the electron pair is again utilized to form a double bond with this carbon, and this electron migrates here. So it will be like this, double bond O with 2 lone pairs, and remaining 2 bond will be as it is with a negative charge at this position. And same way, this charge migrates from ortho position to para position, and from para position it will migrate to again ortho position. And finally it will go back to oxygen to give again phenoxide. So this is how the charge, negative charge on this oxygen is resonance stabilized, and that's why this phenoxide is stable. That's why phenol can lose its proton to form phenoxide, and that's why it is acidic. Now if there are certain substitutions present on this phenol, what will be the effect of that substitution on acidity of phenol? Let's talk about that. Generally, there are 2 kinds of substitutions. We can classify them as one type of substitution. I would say they are electron donating, like methyl group or any alkyl group. They are electron donating. Okay, and other kind of groups which will be present or which can be present on this phenyl ring, they are electron withdrawing groups. Okay, now if electron donating group is present on phenol at any position, the effect produced by these electron donating groups will be positive inductive effect. And that's why, remember this, if electron donating group is present on phenol, then it reduces, or in simple way, it destabilizes the stability of phenoxide ion. Okay, just because the reason is In this case, oxygen has an extra pair, which it is, or oxygen is negatively charged. It has an extra electron. Okay, so that electron or that charge is stabilized by resonance. That means oxygen is giving its electron to this benzene ring. And if we have a group like methyl, which is already present on the ring, which is also an electron donating group, then it diminishes the stability, or it diminishes the electron donating capacity of this phenoxide, and that's why the stability of this phenoxide will be reduced and the compound will be weakly acidic or less acidic. Destabilizes phenoxide and it will be less acidic. I have given you example of methyl. Now, there is second category, compounds or groups which are electron withdrawing. Electron withdrawing like nitro. If groups like nitro are present on this on this phenol, then they contribute in resonance stabilization. How? They increase the number of resonating structures possible. They also participate in resonance stabilization because the effect produced by groups like nitro, it is negative inductive effect or negative resonance effect. Due to this, if electron withdrawing groups are present on phenol, then phenol will be more acidic because they increase the stability of phenoxide. Increase stability of phenoxide and it will be more acidic. Okay, now let's see, because just we can, when we see nitro group, if nitro group is present on this phenol, then it increases acidity, but there are certain limitations. Just because position of nitro group on this benzene, on this phenol is also important. Okay, so effect of position, let's understand this. Effect of position on acidity of phenol. Just first understand, if nitro group is present on this phenol, how it will contribute in increasing the, and nitro group is now present at para position. What will be first step? First resonating structure will be similarly. Okay. This oxygen will form a double bond and two lone pairs will be there. Negative charge will be at ortho position and nitro group is present at para position. This is your first resonating structure. Second resonating structure, bond will be here and these electrons will be transferred at this position. Then this bond is again transferred and these electrons are migrated to this position. So this is what I say, contribution of electron withdrawing group in resonance stabilization of phenoxide. And Finally, this negative charge is migrated to oxygen. So this is how nitro group will help to resonance stabilize phenoxide ion. Okay. Now, this is also only possible, this resonance stabilization or contribution in stabilization of this phenoxide is possible when this nitro group is present at ortho or para position only. If it is present at beta position, then it will not be able to contribute in this manner. Reason, because look at the resonance structures of phenoxide. The negative charge is always present at ortho and para position only. So if nitro group is present at ortho and para positions, then only it will contribute in resonance stabilization, otherwise it will not. Okay, so we can take an example. Picric acid 2,4,6-trinitrophenol. Why picric acid is highly acidic? Because in this case it is a cumulative effect of 3 nitro group present at ortho and para position. That's why it is more acidic or highly acidic than when nitro group is present at para position. Okay, then when nitro group is present at meta position, nitro group is present at ortho position. First 2,4,6-trinitrophenol, this is picric acid, then paranitrophenol, then orthonitrophenol, and then finally metanitrophenol. Groups like NH2 and methoxy, what is their effect on acidity of phenol? If groups like these, they are present at para position in phenol, if groups like these, they are present at para position of the phenol, then the effect exerted by these groups is positive R and negative inductive effect. Okay, now in this case, this positive R effect is more or greater than negative inductive effect. It is a stronger one. So their presence at para position decreases the acidity. It decreases acidity. If groups like NH2 and methoxy, they are present at para position, then para position of phenol, then it reduces acidity. Okay, if these groups, they are present at meta position, they are increases acidity. Okay, this is just because they produce negative inductive effect only. So again, this is what we have to remember, and that's why from this, okay, from this I would say Meta-methoxy phenol is more acidic than phenol. This is the trend which we have to remember. Phenol is more acidic than orthomethoxy phenol, which is more acidic than paramethoxy phenol. Completely different from nitro group. That's why I am mentioning this. You have to remember both these groups. If they are present at para position, they produce weakly acidic compound, weakly acidic phenol. If they are present at ortho position, the acidity will be little bit more. Okay, and if they are present at meta position, then the compound will be, or the phenol will be highly acidic. Okay, so this trend you have to remember. Okay, so that's it about effect of substitution on acidity of phenol. Thank you.